Hello students. So previously we will start a lecture series on mathematical physics. Now you can find some lectures on mathematical physics given previously in from lecture number 204 to 210. You can find some of the lectures. So we'll start at a fresh, and the first topic that we will start with is your vector calculus. The first thing that we will discuss is the angle between two vectors. Suppose you have vectors A and vectors B, then the angle between them is cos theta, and that is equal to A dot B divided by A into B. Now the next, so this is call it number one. The next is condition for coplanarity of vectors. That means if the vectors A and B are in the same plane, then A dot B and ABC are not in the same plane, then A dot B cross C is equal to 0 if they are in the same plane. So this gives you actually the volume. If we have three vectors A, B and C, then the volume created by these vectors is actually the value. So if they are coplanar, so there can be a volume formation because one that has to be x, y and z, three directions. So that is how this is the condition for coplanarity. That means the vectors A, B and C and neither of them are in the same plane. The next point in vector calculus that is number 3 is the del value. So it is represented as del y del xi plus del y j plus del y del z k, and we have a gradient based upon that. So gradient is nothing but if we have a scalar quantity phi, so and it makes a vector quantity out of it. So del phi is equal to del phi by del x I plus del phi by del y j plus del phi by del z k. And if we have a vector quantity, suppose you have a vector v which is equal to vx I plus vyj into vzk. That means it has three components, vx, vy and vz in the three directions x, y and z, I, j, k. So then we have something called a divergence. divergence nothing but del dot V, and it is equal to del by del Vx by del x plus del Vy by del y plus del Vz by del z. It is a scalar quantity. So the next series system, we find now based upon this del operator, we have another operator. It's called the Laplacian operator. Let's call it number 4. Laplacian, it is basically del square. So it now becomes del square by del x square plus del square by del y square plus del square by del z square. If it is a Cartesian coordinate, that means if it is x, y and z coordinate, we can have a spherical coordinate system as well. Spherical coordinate system with r, theta and phi, and we can have a cylindrical coordinate system as well with r, theta and z. The difference between these two coordinates are as follows. Suppose you have a this is, say, the x, y and z coordinate. So this one is z, say this one is x and this one is y. Now in cylindrical coordinate, what happens is that if you form a cylinder, so the cylinder will be formed by a position vector which we call as r. Now this position vector revolves around with an angle, so we call this one as angle as theta, and it has got a certain distance from the base, so that is the z. So r, theta and z. So by variation of this r, this theta and this z, we actually create this cylinder. So it's a cylindrical coordinate system, r, theta and z. Similar to that, we can have a spherical coordinate system as well. So in a spherical coordinate system, if you want to make it create from the zxy system, you need to create a sphere. So to create a sphere, you again require a position vector r, and you require two angles. One is this theta and one is this phi. So we can have a spherical coordinate system by r, theta and phi. So the Laplacian operator can be represented in terms of in a spherical coordinate system as well, and a cylindrical coordinate system as well. So in a spherical coordinate system, that is r, theta and phi, we can represent the Laplacian operator del square as equal to 1 by r square del by del r of r square del by del r plus 1 by r square sin theta del by del theta of sin theta del by del theta and 1 by r square sin square theta into del square by del phi square. This is how we present the Laplacian in spherical coordinate system, and similar to that we can also form the Laplacian in cylindrical coordinate system. So in cylindrical coordinate system, that means r, theta and z, we could represent del square as equal to del square by del r square plus 1 by r del by del r plus 1 by r square del square by del theta square plus del square by del z square. Okay, so this was number 4. Moving on, we will now use vector integrals. We first write with the line integral. Line integral can be represented in the following manner. If it is a scalar quantity, we can represent it by phi dr, where phi is a scalar, dr is a vector, or we can represent it in terms of a dot product. That means it is a dot dr, or in terms of a cross product, that is a cross dr. So this is a scalar quantity, and a is a vector quantity, and this r is the position vector, and it is given as xi plus yj plus zk. Now based upon these integrals, vector integrals, we have two theorems. The first theorem is called, it's number 6, is called Stokes Theorem. It says that a closed integral, a line integral A dot dr is equal to the surface integral del cross A dot n ds, which is actually equal to, in a simplified manner we can write as del cross A into dot ds. This line integral of the tangential component of a vector, this is called the tangential component A dot r, taken around a simple closed curve C, is equal to the surface integral of the normal component of the curl of the vector. This is called curl, and the normal component means dot, n means its normal component taken over the surface having a C as its boundary. This is the Stokes theorem. And another theorem based upon vector integrals is called a divergence theorem. So according to divergence theorem, the volume integral of a gradient, the volume integral of a divergence is equal to the gradient or is equal to the surface integral of the tangential of the normal component of a vector. So it's how a volume integral is now being reduced to a surface integral. So this is a volume integral and this is a surface integral.